All right, welcome back. In this video, we're going to look at uh, another case that involves a second order linear differential equations with constant coefficients. But this time, we're going to be looking at equations that are non-homogeneous, right? Let's get right into it. So here's the overview. So we're going to consider the following equation, right? A times y double prime of t plus b times y of t plus c times y prime of t time, plus c times y of t equals some function in t, capital F, right? So we know different techniques of solving the corresponding homogeneous equation, right? A times y double prime of t plus b times y prime of t plus c times y of t equals to 0. And that solution, it's going to be called the complementary equation. So the solution to this homogeneous equation, it's going to be denoted by y sub h of t, okay? So the challenge here is to incorporate this f of t somehow, right? And that will come about by formulating what's called a particular solution, right? So it's a solution that is made in the context of using this function f of t. So a solution y sub p of t, okay, to this differential equation as a whole, right? It's what's called the particular solution, right? So, and then in this part right here, this reflects on the principle of superposition, right? So if we have two set of solutions to this differential equation, right? Then the general solution will look like this, and it's also a solution for this equation as well, right? So yeah, so if we know that it's a solution, right? We'll just I'll just show you, right? So if we suppose that y of t is this function, right? Y sub h of t is the solution for the homogeneous equation. Y sub p of t is the solution for this equation, right? We'll have a times y sub h double prime of t plus y sub p double prime of t plus b times y h prime of t plus y sub p prime of t plus c times y h t plus y p of t is 0, is a capital F of t. Capital. It has to equal to capital F of t. And so this would equal to, we'll have h a times y and then we'll have plus y p of t plus b times y, so p prime of t plus c y prime of t. Since y sub h of t is a solution for the homogeneous equation, this would be 0. And since the particular solution is a solution for the differential equation here, right, this would equal to capital F of t, right? So this would equal to capital F of t. So what we're gonna do is so we know the steps to solving the homogeneous equation. What's going to be a challenge is solving for the function y sub p of t. Okay. And the best way to do this is going over some examples. So here's one now. So I'll do this one first. So we want to figure out a general solution for the following differential equation, right? So we have this equation on the left, and this would equal to the function on the right. I should point out that this method will only work for a certain subset of functions. Okay, so and also this would also work if you have a differential equation, right, in this form. Right, you have a polynomial, you have a differential equation of a pth order on the left-hand side, exclusively in y, and you have on the right-hand side as another function in t, right? So this method would work for functions like polynomials, right? We have this would work for exponentials, and then certain trig functions, or a combination of a product of these functions here that would work. Okay, so let's actually go over this example now. So what we do first is solve for the homogeneous part of your general solution. So the way we do this is figure out the characteristic equation. So in this case, it's r squared minus 4 times r minus 12 is 0. Okay, this is factorable, so we'll have a r minus 6 times r plus 2 is 0. And so, Jesus Christ. So we'll have r is equal to 6, and then r equals -2. And so the homogeneous counterpart, so the homogeneous solution, this would be C1 times e to the 6t, and then plus C2 times e to the minus 2t. Okay, e to the minus 2t. Now the next step is to solve for the particular solution, right? Solve for what y sub p of t is. So on the right-hand side, we have 3 times e to the 5t, okay? So we need to incorporate this type of function into our differential equation in some way, right? And also for y sub p of t, it doesn't have any arbitrary constants. That's the goal. So what we're going to do is guess what function it could be. So since we have a e to the 5t on the right-hand side, what we're going to do is we're going to let yp of t equal to some constant a times e to the 5t. Okay, times e to the 5t. So now, if we do that, so a is a constant, and we want to solve for a in this case. So yp prime of t, this will equal to 5 times a times e to the 5t, right? And then the second derivative, this would be 25 times a e to the 5t. And so from here, we're going to solve for what the constant capital A is. So by the differential equation, what we have is we'll have 25A times e to the 5t minus 4 times yp prime of t, which is 5a e to the 5t, minus 12 times yp of t. So minus 12 times a times e to the 5t equals to 3 e to the 5t. Okay? So what we have now is we'll have 25a e to the 5t. So we'll have e to the 5t times 25a minus 20a minus 12a equals 3 times e to the 5t. Okay. So we have so minus 7a equals to 3. So therefore a is equal to negative 3/7. Okay, negative 3/7. So therefore, the general solution will be y of t equals to c1 e to the 6t plus c2 e to the minus 2t minus 3/7 e to the 5t. And that's your answer. Okay? So hopefully that made sense. Okay? So I'm just going to go over another example. Okay? So it's going to be the same equation on the left-hand side. All right, but what's going to be different is what the right-hand side equals to. So here we go. So now we have a polynomial in terms of t. Okay. So we have a polynomial on the right-hand side. Okay. So we already know what the left-hand side equals to, right? So if I just go back, so the left-hand side looks like this, right? So YH of t is equal to C1 times e to the 6t plus C2 times e to the minus 2t, right? So that's the homogeneous term. But what's going to be different is the particular function, y sub p of t, okay? So we know this right-hand side is a polynomial in t, okay? So what we're going to do is formulate y sub p of t as a cubic function. Okay, so y sub p of t would be a times t cubed plus b times t squared plus c times t plus d. Okay, so our particular solution would be in the form of a cubic function, right? And so yp prime of t, this would be equal to 3at squared plus 2bt plus c. And then yp double prime of t, this would equal to 6a times t, and then plus 2 times b. Okay? All right. So what this means by the differential equation, what we have is what this implies is y double prime is sits A t plus b minus 4 times y prime, which in this case is 3a t squared plus 2bt plus c minus 12 times y of t. It's at cubed plus bt squared plus c times t plus d. And that has to equal to 2 times t cubed minus t plus 3. All right. So this is where the real work comes in. Let me get rid of this. Oh, God. Okay, so what that means is, okay, so first of all, I'm going to find the I'm going to find the t cubed terms. So we have this term here along with minus 12. So we'll have a minus 12a t cubed. Next, I'm going to find the t squared terms. So we'll have this term along with the minus 12, and then this term along with this term here. So we have a minus, so this is t squared. So we will have a plus minus 12a. And then, oh, I'm sorry, minus 12b. I got to be careful here. Plus, shoot. Minus 12a t squared. Okay. All right. Next is the t terms. Be with this guy. And it will be this guy and this one. So that's plus. So we'll have a 6a minus 8b and a minus 12c times t. And then the constants. All right. So we'll have, so sits b minus 4c minus 12d. Those are the constants. And this polynomial has to equal to 2t cubed minus t plus 3. All right. So since these polynomials have to equal, their corresponding coefficients have to equal. So what that means is minus 12a equals to 2. That's the t cubed coefficients. The t squared coefficients would correspond to minus 12b minus, oh God. Minus 12a minus 12b equals to 0. The t coefficients, so we'll have a 6a minus 8b minus 12c is equal to -1. And then the last one, the constant, 6b minus 4c minus 12d is 3. Okay, it's 3. So by equation 1, we know that a is equal to -1/6. Okay, and by equation 2, we'll have, so since A is -1/6, we'll have 6 minus 12B is 0. And so that means that B is equal to 1/6. By equation 3, we know that A is -1/6, so we'll have a -1. B is 1/6, so that is 4/3. -1 minus 4/3 minus 12C is equal to -1. So we'll have that C is equal to -1/9. Okay. And then by the fourth equation, you should get that D is equal to -5/27, right? 5/27. All right. Okay. So now, since the hard part's over, we know what the particular solution is. Y sub P of T, that's T thick. So Y P of T, this would equal to -1/6 T cubed plus 1/6 T squared -1/9 T cubed minus 5/27. Oh God, I meant T. This is a constant. Okay, so this here's the particular solution. And so therefore, the general solution is equal to C1 times e to the 6t plus C2 times e to the minus 2t minus 6t cubed plus 1/6t squared minus 1/9 t minus 5/27. Okay, so that's your answer. All right. Let's look at another example. This one here. We want to figure out a general solution for this differential equation. Okay. So first of all, and if you want to try it, pause the video, okay? But the characteristic equation, so we have to solve for the homogeneous equation, solve for y sub h of t. So, okay, so that would correspond to r squared minus r plus 9 is 0. Okay. Okay. So the factors for 9 is 1, 3, and 9. Okay, and there's no way we can figure out how we can get a sum of -1 by using those three numbers. Okay, so we're going to use the quadratic formula. So r is equal to 1 plus or minus the square root of -1 squared minus 4 times 1 times, so 9 over 2. So r is equal to 1 plus or minus. So in this case, it is the square root of 35 times I over 2. Okay. Yeah, okay. So now the homogeneous solution, y sub h of t. I'm gonna need more room. So, oops. Come back to that later. So the homogeneous function, this will be equal to C1 times e to the t over 2 cosine of root 35 over 2 plus C2 times e to the t over 2 times sine of root 35 over 2. Okay, so that's the homogeneous equation. So now the second step is to solve for the particular function y sub p of t. So now, this time we have a term that has sine of 3t in it, okay? So in this step, you can disregard the constants, right? So what's really important is if the right-hand side contains either a polynomial or an exponential function or a sine or a cosine function, or a different combination of those functions, right? Okay, combination, I mean product, right? So since we have sine of 3t, our particular function will be a sum or a difference of families of sine of 3t and then cosine of 3t. So in other words, y sub p of t, this would equal to capital A times cosine of 3t plus capital B times sine of 3t, right? Okay. And so we're going to use this function here. Oh, Jesus. We're going to use this function as the particular function to plug into our differential equation and then and solve right away for the general solution. So y p prime of t, well, this would equal to minus 3a times sine 3t, okay, it's plus 3b cosine 3t, and then yp double prime of t. This would equal to minus 9a cosine 3t minus 9b sine 3t. Okay. All right. So we have that. Okay. So we have that. And okay. So now all we have to do is plug the functions here into the differential equation and then solve for the constants capital A and B. So y double prime, that will correspond to saying, should probably write it down here. So I have a minus 9a cosine 3t minus 9b sine 3t. Okay, minus y prime. And then this is a plus 3b cosine 3t plus 9 times y of t. And this equals to 3 times sine 3t. Okay. So that left-hand side is equal to 3 times sine of 3t. Okay, so first of all, let's gather the cosine terms. So we have a cosine here, we have a cosine here, and we have a cosine here, multiplied by 9. So we have a minus 9a, and then a minus 3b, and a plus 9a. cosine 3t. And next, we're going to add in the sine terms in this one here. So we'll have a plus minus 9b plus 3a and then a plus 9b. And this has to equal to 3 times sine 3t. All right, so what we have is um, so what we have is so the cosine 3t, so we'll have a minus 3b is equal to 0. So if we match up the coefficients that correspond to the cosine and sine functions, so we'll have a minus 3b equals to 0. And by equating the sine of 3t terms, we will have that 3a is equal to 3. So this says that b is 0 and then a is 1. Okay? A is 1 and b is 0. So that means the general solution would be equal to C1 times e to the t over 2 times cosine of root 35 over 2t plus C2 e to the t over 2 times sine root 35 over 2t. And the a is 1. So we'll have a plus sine of 3t. And that is your answer. Okay. So hopefully that makes sense. And so I'm going to give out just a brief overview on how we would choose the particular function y sub p of t. Okay. So here is just a few tables and some examples. Okay. So so this table on the left, this would correspond to the on the right hand. Let's see. So this table right here, this would correspond to the equation on the right. So if we have this equation, okay, and then y, of course, is some function in t, right? So not capital F of x. This is a capital F of t. Ft. All right. So yeah, so if your right-hand side is alpha times e to the beta times t, right, you would use an exponential. Okay. If your right-hand side involves a constant times a cosine or a sine function of some kind, you would use this as your particular solution, right? Your particular function. Okay. And then if you have a polynomial in terms of x or t, the delta is just a constant, right? You would use this, okay? If you just deal with a polynomial exclusively. But this last property here is if you have a polynomial times an exponential function, right? So you would use the same polynomial that's used up here previously, but you just multiply that polynomial by e to the beta x, right? So, And here is just some examples just to clarify on what you would use as your particular solution, right? So yeah, so if you have any constant, right, you would use A. If you have a quadratic, you use this form as a particular solution. If you have a cubic, if you have just a product of a polynomial and an exponential function, you use this. Or if you have a product of an exponential and a trig function, you use this, okay? And if you have a product of a polynomial and a trig function, okay, you would use this. Notice here, right, it's a different set of different types of quadratic polynomial, a quadratic trinomial, right, in combination with a cosine and a sine function, right? So yeah, just try to read these examples very carefully to see what form you would use as your y sub p of x, okay? And to wrap things up, I want to do one more example, okay? So with that, I want you to try to figure out a general solution for this differential equation, okay? Y double prime plus 4 times y equals to sine of t minus cosine t, okay? So if you want to try to work on this example, pause the video because, but otherwise I'm going to explain this right now. So first of all, we want to find y sub h of t, right? So that would correspond to solving for the characteristic equation, r squared plus 4, r squared plus 4 is 0. So that means r squared is equal to -2. So r is equal to, I'm sorry, -4 plus or minus 2i, right? You can't see that. Okay. And so the homogeneous function, this is C1 times cosine of tt plus C2 times sine 2t. Okay. And the other part is solving for the particular solution. Now, we notice on the left-hand side, we have a difference, right? Sine of t minus cosine t. Now, the t's are they have the same quantity inside the sine and cosine function, right? So since that is the case, we can write out y sub p of t as just a times cosine of t plus b times sine t. Okay, just like that. And so then yp prime of t is equal to minus a times sine t plus b times cosine t. And then the second derivative would be minus a cosine t minus b times sine t, right? Okay, so okay, so now, so if I label this differential equation star, what that means is y double prime is so minus a times cosine t minus b times sine t. plus 4 times y of t. So that is a times cosine t plus b times sine t. This would equal to the right-hand side, sine of t minus cosine t, right? And so what this means is, let me erase this. We wrote those down. So what that means is if we match up the cosine terms, we have a minus a and we have a plus 4b. I'm sorry, that's sine. The cosine term is right here. So that would be a 3a cosine t, right? And if we have the sine terms, we have a minus b and a plus 4b. So that is a 3b sine t. And that has to equal to sine t minus cosine t, right? And so since these quantities are equal, their coefficients have to equal. So in terms of the sine terms, we'll have a 3b equals 1. And we have, by the cosine terms, we have 3a equals -1. So that means b is 1/3. And then a is equal to -1/3. Okay. So therefore, y of t, the general solution, looks like C1 times cosine of 2t plus C2 times sine 2t minus 1/3 cosine t plus 1/3 sine t. And that's your answer. Okay? So that about covers this lesson on solving non-homogeneous second-order differential equations. So for the next set of videos, we'll talk about another method called using a variation of parameters. And then talk more about on and now we'll also talk about variable coefficient equations, okay? And then very soon we'll get into Laplace transforms. That's going to be great. So with that, there's your comprehension problems. If you have questions, please let me know. But hope you enjoy this video, and I'll see you next time.